Okay. Hi, everyone. So today we are going to talk about Fermat's little theorem and how it relates to RSA. Okay, so remember we talked about Fermat last time. So what it says is, so Fermat's little theorem says if P is a prime, A is not congruent to 0 mod P, then A to the P minus 1 is always congruent to 1 mod P. Okay, so example, so if you have P equal to 5, A equal to 2, okay, then this says 2 raised to the power of P minus 1, 5 minus 1 must be congruent to 1 mod 5. And 2 to the 4 is 16, which is 1 mod 5. Right? Okay, so if you want to verify Fermat for A equal to 2 and P equal to 5, what you would do is raise 2 raised to the power 4 and see that it's 1. But the way Fermat saw it was very different. Okay, and that's a hint to how he proved it. So here's how he saw it. So he said, well, let me look at the numbers mod 5, which are not 0. So there's 1, 2, 3, and 4. Right? So he looked at the numbers 1, 2, so on up to P minus 1. Right? 0 he left out because it's 0 mod 5. And then he said, well, let me try mapping these. So let's map these to the set 1, 2, 3, and 4. And the way he mapped them is by multiplying each one by 2. Okay, so 1 times 2 is 2. 2 times 2 is 4. 3 times 2 is 1. Right? Mod 5. 3 times 2 is 1. 4 times 2 is 3. Okay. So that doesn't seem terribly spectacular. So, well, except that, every one of them went to a different element. But even then, so what? Well, you see, now he said what he was looking at was 1 times 2 and 2 times 2 and 3 times 2 and 4 times 2. Now, what if you take all of these and multiply them together? So you get 1 times 2 times 2 times 2 times 3 times 2 times 4 times 2. Okay. But then what do you get in the end? Well, you get 1 times 2 is 2. 2 times 2 is 4. 3 times 2 is 1. 4 times 2 is 3. Okay, so now you just take these out and you say, well, you have 1 times 2 times 3 times 4 here, and you have 1 times 2 times 3 times 4 here, so you can cancel those out. So you cancel out 1 times 2 times 3 times 4 from both sides. And what are you left with? You're left with 2 times 2 times 2 times 2. Right? So you have 2 to the 4 must be 1. Okay, so that was his proof. Do you believe this? Okay, so let's try it again, except we'll try it with general P and general A, right? So let's try the same proof again. So we are trying to prove if GCD of if A is not congruent to 1, A is not congruent to 0 mod P. Okay, A is not congruent to 0 mod P. Meaning what? Meaning, well, if A is not congruent to 0, then the GCD of A and P must be equal to 1, right? P is a prime. Okay? So now, what do? Well, we line up the numbers 1, 2, all the way to p minus 1. We line up all the numbers 1, 2, all the way to p minus 1. And then we take each of these and multiply it by a. So when we multiply 1 by a, we get a. And then we multiply 2 by a, we get something. Maybe we get 2a, it may wrap around. Okay, we get something. So maybe it goes here, 3, it goes there, 4, it goes somewhere else. Okay, so it just does that, right? Now, the claim is this must be a bijection. So multiply by f of x equal to x times a times x mod p is a bijection on the set 1 through p minus 1. How do we know that? Well, you see, if you multiply by a, you can also have the inverse map where you go backwards. So how do you go back from, if you're multiplying by a to go forward, how do you go back? Multiply by a inverse. Right? So you have a map g of y equal to a inverse y mod p. And this has the property that if you do f of x and then you do g of that, you get a of x, and then you have a inverse mod p. And that's just, these cancel, and you just get x. Right? Same thing if you do f of g of something, then you get back whatever it is. Right? Okay, so it's a bijection. Bijection meaning each of these hits exactly one thing here, right? So each element here is hit by exactly one of these guys on the left, right? Meaning each one is hit and it's hit once. Okay. So now we go ahead and multiply the things on the, that we are starting with. So we multiplied each one by a. So we multiplied 1 times a, or a times 1, times a times 2, times a times 3, times so on, a times p minus 1. And then what did we hit? What were the things equal to? Well, a times 1 was something here, a times 2 was something else, but everything here got hit exactly once. Right? So we're saying, well, what we got here was the same thing as 1 times 2 times so on up to p minus 1. It was 1 times 2 times so on up to p minus 1 mod p. Okay, so now the next thing we do is we say this left-hand side, this is the same thing as saying, a raised to power p minus 1 times 1 times 2 times so on up to p minus 1. Right? And now we want to cancel the 1 times 2 through p minus 1 from both sides and say a to the p minus 1 was 1. So what gave us the right to cancel this out? Why could we cancel them? Maybe that's where there's a problem in the proof. Yeah. Yeah. So it looks okay, doesn't it? Because p is a prime. So everything is which is not 0 mod p has GCD 1 with p. If it has GCD 1 with p, then there's an inverse. So you can cancel 2's from both sides because 2 has an inverse. Right? You can cancel 3's, you can cancel 4's, you can cancel all the way to p minus 1. So it's okay to cancel all of these. So once you cancel all of these, all you're left with is a to the p minus 1 is congruent to 1. And that's Fermat's little theorem. how did we know it was a bijection? So remember, we said something about bijections. To prove that f is a bijection, it suffices to show that there's an inverse. Right? There's a g which is an inverse of f. What does it mean it's an inverse? Well, if you apply f first and then g, you get back to where you started from. If you apply g first and then you apply f, you get back to where you started from. So we said, well, f of x is a times x. Right? But now we can make g of y be a inverse times y. And so when we multiply it by a inverse, we are undoing the effect of multiplying by a.
And we know that a inverse exists because there used to be a theorem.
That's right. That's right.
Is that sufficient to prove that the inverse or g of y exists?
Well, in this case, yes, right? Because g of y is just multiplying by a inverse. Huh? Yeah.
Why do you define fx equals a times x not like a to the factor of x?
Why did we define a times x rather than a to the power of x? Oh, why didn't we define it a to the power?
The theorem is like 2 to the like 4 to the power of
It's like a raised to the power of p minus 1. Yeah, so why did we define it as a times x? Well, see, yeah, it's yeah, good question, because it I mean, it's a, you know, do you see that a times x does work, and it works because it proves a bijection, whereas a to the x, we don't know what we do with that, right? A to the x we have no control over, right? Now, the thing about this theorem is, this proof is, it's actually quite, I mean, given its generality, given what it's saying, you look at the proof and it's so simple. Right? It's so simple, and yet it's, you know, it's not clear how anybody ever thought of it. Yeah? So, you know, earlier today I was reading the news, and it turns out today would have been Steve Jobs' 60th birthday. And so they had a bunch of quotes from him. And one of them was particularly interesting to me, given that, you know, we are going to do Fermat, because it was a quote from him saying, I wish I remembered it exactly, but it was something like, you know, one of the things that Steve Jobs was very interested in was making things simple. Right? Simple was very important. And so this quote said, you know, that simple is sometimes the most complex thing to do. Right? You have to work very hard to make things simple. And, you know, this is one of these things which is incredibly simple, but you have the feeling it has the making of a, you know, this is pure genius there. Right? Okay, so now where do we go from here? So from here we go directly to RSA. So before doing that, let me just state Fermat's theorem in a slightly different form. So instead of saying if p is a prime, a is not congruent to 0 mod p, then a to the p minus 1 is congruent to 1 mod p. We'll state Fermat in a slightly different way. We can say, another way of saying it is, for all a to the power of p is congruent to a mod p. Right? So once we've proved Fermat in that other form, do you see that this one is, it's clear, right? It holds. Anyone not see that? Okay. Okay, so now let's go back and look at the RSA cryptosystem. So in the RSA cryptosystem, we had two parties, Alice and Bob, or Amazon and Bob, as the case may be. Now, in this case, what we had was Alice picked two primes, P and Q, and multiplied them together to get a composite number n. P and Q were large primes, right? About equal number of digits, so, okay. And then what Alice did was pick two numbers, E and D, in a certain way. To pick E and D, she had to know the prime factors of M. But then what she publishes is N and E, and what she keeps private is D. Okay, once all this is done, she can throw away the prime factors if she wants. And now, if Bob wants to send Alice a message, in order to encrypt it, so the message is going to be a number mod n. So Bob wants to send a message m between 0 and n minus 1. And so what he does is he encrypts this message by raising m to the power of e mod n. Call this x. Okay, so this is the ciphertext. This is what he sends to Alice. And now what Alice does is she raises x raised to the power of d mod n, and this should turn out to be m. Okay, so now if you work through this, you realize that x raised to the power of d is m raised to the power of e whole raised to the power of d mod n, which is the same as m raised to the power of d times e mod n. And so the property we want from RSA is that for every m raised to the power of d times e is congruent to m mod n. Now you should be able to see that there's something very similar about Fermat's little theorem and about this RSA property. Okay? And that'll show us how we should pick D and E. So before we do that, I want to strengthen this just a little bit more. Okay, so instead of writing it in this form, let's write it. We can also write a raised to the power of k times p minus 1 plus 1 is congruent to a mod p for any integer k. Right? Is it clear that you can do that? I'm sorry? No, it's not clear. Okay. So why is a raised to the power of k times p minus 1 plus 1 congruent to a mod p? As long as p is prime, right? So for all a. Okay. So what's this saying? So first of all, if a is congruent to, so there are two cases. A is congruent to 0 mod p. Then do you believe this claim? 0 raised to the power of anything is 0. Yeah? Okay. Case 2. A is not congruent to 0 mod p. now we can use Fermat's little theorem from up there. So a raised to the power of k times p minus 1 plus 1 is what? Well, it's a raised to the power of k times p minus 1 times a. Right? Because I just pulled out the plus 1. And then what's a raised to the power of k times p minus 1? Well, when you have a product like this in the exponent, you can take a raised to the power of one thing, whole raised to the power of the other, right? So you can write this as a times a raised to the power of p minus 1 whole thing raised to the power of k mod p. Okay, now what's a raised to the power of p minus 1? That's 1 by Fermat. What's 1 raised to the power of k? It's 1. So this is a. Okay, so what Fermat is basically telling us is, as you raise a to high, as you raise a to higher and higher powers, you cycle back. And how often do you cycle back? Well, every p minus 1 steps. Right? You start with a, and then after p minus 1 steps, that's how long it takes you to cycle back. Okay? So now, what we want to do is we want to figure out, if we are working mod n, how long does it take us to cycle back? Okay? When p is a prime, we know exactly when we cycle back. It's after p minus 1 steps. So when do we cycle back mod n? And the answer is, well, it depends upon the prime factors of n. Okay, that's where the fact that Alice knew the prime factors came in handy, right? If you're given the number n, you have no idea when it cycles back, but if you know the prime factors, you know when it cycles back. And so if n is equal to p times q, then it all cycles back after p minus 1 times q minus 1 steps. That's how long it takes. Okay? And so what we want d times e to be, in order to make m raised to the power of d times e congruent to m, we want to make, just by drawing an analogy with Fermat, what we want is d times e to be equal to k times p minus 1 times q minus 1 plus 1 for some k. We don't care what k is. Okay? So how does Alice pick her keys? How does Alice pick D and E? Well, what she does is she just selects, what is this condition saying? Another way of writing this condition is D times E is congruent to 1 mod P minus 1 times Q minus 1. Okay, that's the RSA condition. That's what D and E have to satisfy. So all Alice has to do is, once she has picked n, she picked the primes P and Q, multiplied them to get n, but then she keeps the primes around to compute P minus 1 times Q minus 1. Okay, so she computes this. It's hard to figure out P minus 1 times Q minus 1 if you don't know the prime factors. In fact, if you know both n and these prime factors, P minus 1 times Q minus 1, you can figure out P and Q from that. Okay, so it's as hard to figure this out from n as it is to factor n. Okay? All right, so she happens to know the factors. So she knows P minus 1 and Q minus 1. Now, all she has to do is pick two numbers D and E so that their product is 1 mod P minus 1 times Q minus 1. In particular, it means that D and E have to be relatively prime to P minus 1 and Q minus 1. Okay? Now, usually, what you do is you choose E equal to 3. But if you choose E equal to 3, you have to make sure that E3 does not divide P minus 1 and it doesn't divide Q minus 1. But that's what you usually do in RSA. Now, why would you ever do that? Well, one reason you do that is because in order to encrypt, you're taking a message and raising it to the power of e. Okay, cubing is actually an easy thing to do. When you raise to the power of 3, it's easy. Raising it to a much higher power takes more work. So you want it to be the smallest power that you can get away with. You can't get away with 2 because, well, why can't you get away with 2? Why can't e be 2? Yeah, so p minus 1 and q minus 1 are even, right? These are large primes. They're odd. P minus 1 is even, so you can't pick 2. Okay? So that's the smallest number that works, and that's often what's used. But you can use anything you want as long as it's relatively prime. And then you compute d is congruent to e inverse mod p minus 1 times q minus 1. So this is what Alice does. This is how she creates her private key. Okay. So now it remains to see, why does this work? Okay. Well, we want to show that m raised to the power of d times e must be congruent to m mod n for every m. Okay. Another way of saying this is m raised to the power of d times e is what? K times p minus 1 times q minus 1 plus 1. This is the left-hand side. We bring m over to this side. Minus m is congruent to 0 mod n. Right? This is m raised to the power of d times e. Minus m is congruent to 0 mod n, meaning that it's divisible by n. So n must divide this. So we have to, in order to show that this is true, we have to show that n must divide this. Okay, so we are saying this implies that. In order to show this, it suffices to show that both p and q divide this. Right? In order to show that n divides this, we should show that p divides this and q divides this. Okay, so how do we show that p divides this? So we are claiming that p divides m raised to the power of k times p minus 1 times q minus 1 plus 1 minus m. Isn't that just Fermat? Sorry, all I'm doing is, I'm saying Fermat is saying, I could move a to this side, so I say minus a is congruent to 0 mod p. Another way of saying it is that p divides this. Right, that's Fermat. And that's what we have here, right? P divides m raised to the power of k times p minus 1 times q minus 1 plus 1 minus m. Sorry, it doesn't look quite right? This was k times p minus 1. Here we have k times p minus 1 times q minus 1. So is that a problem? So is it a problem that we have a q minus 1 here? No? Yeah. Oh, it's not a problem. So why not? Yeah, so this was true for every k, right? So just take k times q minus 1 and call that the new k, right? So call that k prime, and then it's of the same form, right? So it's just p minus 1 times anything plus 1. That's what we are saying here. It's p minus 1 times anything. So this is anything, right? It's something.
I'm sorry, I still don't get get that if you choose p minus 1 and p minus 1, then it works. But how did we get to there?
How did we get there? Okay, yeah, no, good question. So the question was, it's clear from this that p minus 1 times q minus 1 works as the length of the cycle. But how did we know to make it that? Well, there are different answers to that. One of them is, this is what your homework was getting at, the Chinese remainder theorem. So we're saying, well, look, if you're working mod n, it's like working mod p and mod q. Right? So if you're working mod n, then somebody could be working on the side for you, and they are doing the bookkeeping. And instead of working mod n, they can work mod p and mod q, and it's the same thing. Right? They keep the answers mod p and q, and whenever you want, they can combine them together and get the answer mod n. Right? So now, what are we saying? Well, we have one cycle which is for p. It's every p minus 1. We have another one for q, which is every q minus 1. And so you put these together and you get this p minus 1 times q minus 1. Yeah? Okay. That's one answer. The other answer is, this is sort of a tip of an iceberg. Right? So this is, this is stuff that you learn in group theory or abstract algebra. And in some sense, it's an invitation for you to take such a course in abstract algebra. Okay. So just as an example, we could have n equal to 5 times 11. So this is what Alice might choose. So p minus 1 times q minus 1 is 4 times 10, which is 40. And now she needs to pick an encryption exponent and a decryption exponent. So she might pick e equal to 3 because it's relatively prime to 40. And then what does she choose as d? D is equal to 3 inverse mod 40. What's 3 inverse mod 40? Well, 3 divides 81. Okay, and so d is 27. Right? 27 times 3 is 81, which is 1 mod 40. Okay? So now, if you choose some message, you choose a message mod 55. Okay? So you choose some message m equal to, 7. Okay, so the encryption of m would just be 7 raised to the power of 3 mod 55, which, I don't know, I'm scared to do this, but what is it? 7 sevens are 49 times 7. I'm sorry? Oh, 343, okay, thank you. 343 mod 55, which is, it's 13, isn't it? And then there's something. Is it, or did I get it wrong? It's right. Okay. Okay, and then if you want to decrypt, okay, so would be 13 raised to the power of 27 mod 55, and at this point we give up and we just say, well, we hope it's back to 7 and. Okay. Okay, now, there are a few things to remember when you're using RSA. Okay, so when you're using RSA, of course you can use it like this, but you'd never use it like this. You'd never just take your message and raise it to the power of e mod n. That would be a terrible idea. So why would it be a bad idea? How many of you saw The Imitation Game? Oh, so you know why it would be a bad idea, don't you? Well, because, the point is, well, one of the easiest answers is, what if you had to send the same message again? Suppose your message was yes, or see you for lunch, or something, and something sort of something that you would say more than once, right? And it's something terribly important, so you want to keep it secret every time you say it. Okay, so of course, if you encrypt that message and you encrypt it again, you get back the same ciphertext, the same encrypted message, right? You always send the same string. How could it not be the case that you always send the same string when you're trying to send the same message? How could you possibly avoid it? Yeah. Yeah, you add some random bits to it. Okay? In security, it's called salting. Okay? Okay, it's called salting. Okay. So you take your message, and instead of taking the message mod n, you take it to be half the length of n. So that's about square root of n, right? Mod square root of n. Is it? Yeah. Okay. And then for the rest of it, you put in some random string. Okay. So and you take this mod n. So what I'm saying is, if this was a little n bit number, right? So if n is about 2 to the little n, right? So this is n bits. So now let the message just be n over 2 bits, and then you add salt for n over 2 bits. So that's a random string. So now if you and then you encrypt this, okay, and you send it across, and then when it's decrypted, the person at the other end knows that they have to strip off this, the n over 2 most significant bits and leave, this is the message. Right? So they can do this. They know that that's what you're doing. But now, every time you send the message, you're going to be putting in a different random string here. And so it's okay. Nobody who is eavesdropping would know that you're sending that same message. It's not just when you have the same message, when you have related messages, or, the question is, what if M happened to be some special character? So, for example, suppose you were trying to send the message 0 or 1. You're just trying to send a 1-bit message, right? You're trying to send instructions, do it or don't do it, buy or don't buy, something like that, okay? What if you just did the encryption without this random string? So your message would be either 0 or 1. And then when you encrypt it, what's the encryption of M? The encryption of 0 is 0, the encryption of 1 is 1. That's not terribly secure. Okay? So that's another reason why we want to add this, right? Because we might have a message which is particularly simple. And then who knows which are the simple messages, right? So we just add in the randomness, and then that leads to security. Okay. Okay. So there are many tricks like this that people who use RSA actually know about, and then that's what you actually do in terms of using it. But this is the basic scheme. Okay. And then there are simple embellishments on top of it. Okay. Let me just say one more thing quickly. This has to do with so once you have a public key cryptosystem, it actually gives you a lot more information. It gives you the possibility of doing many, many, many things with it. Okay, and some of these things you will actually explore in the homework, including the virtual lab, okay, which basically is something called a bit commitment scheme. But then also in the homework you'll explore something called a digital signature. Okay, so So the point of this is that a public key cryptosystem is an extremely powerful object. And, once you start thinking about how to use it, there are many possible uses of it. So one of the uses of it is, suppose you have a document and you want to sign it. Okay? You want to sign it, meaning, so what's the property of a signature? So when you put your signature on a document, what you're saying is you're attesting to the fact that you are the one who, that somehow you've agreed to this document. And your signature there makes sure that nobody else could have forged that signature. Okay? So now, if you look at a public key cryptosystem, there's one thing there that Bob can do, and he's completely, there's a guarantee nobody else could have, Alice can do where there's a guarantee nobody else could have done it. And that is decrypt, right? So if you look at the decryption function, d of x, right? If you can say that x was decrypted, right? If you have a document x, so if x was some document, and you manage to get it decrypted by Alice, that's like a proof that she really attested to this document. Okay? And so that's like a signature that, because you can say, well, nobody else could have decrypted it. Okay? So that's the basic idea behind a digital signature scheme. Right? You have when you actually sign, you're sort of saying, here's a squiggle that nobody else knows how to make. Only I do. Okay? It seems like a pretty flimsy sort of thing to have. But then you look at something like this, where you have a function that only you can, only you can compute. And the reason only you can compute it is because you happen to pick the primes and multiply them together and create this composite. And nobody else knows what these primes are. And as long as they don't know the primes, they have no idea how to compute this function. Okay? Okay, so that's the basic idea behind a signature scheme. In your homework, you're asked to sort of say, well, spell it out a little further and say, well, how do you make it really secure? Because right now, it may or may not be secure. There are certain problems with it. How do you deal with that? Okay? Okay, so let's see. Any questions? Yeah. I'm sorry, what if what? Oh, well, see, no, so, okay, so sorry. Okay, let's just see. What do we need from a signature scheme? What we need is, okay, so Alice can sign. Okay, so Alice can sign because she knows her decryption function. But now anybody else can verify that this is a signed document. Right? How would they verify that this is a signed document? So suppose that I claim that this is a signed document that Alice happened to sign. How would you actually verify it? Yeah. You could encrypt it back. Right? So once you encrypt it back, you get back X, and that's your document. And that's your proof that it was decrypted. Right? Because this is a bijection. RSA is a bijection. So once you know that X maps to D of X, you know that, right? Once you know that D of X maps to X under encryption, you know that X maps to D of X under decryption. So you're using the RSA property, that it's a bijection. Yeah.
Are you using like the decryption as in encryption?
You're using the decryption as a signature, right? And then the encryption is the verification of the signature. Yeah.
Does that give any hints about what the encryption
Well, the encryption key is known to everybody. Right? The question is whether the decryption gives you some hint about the decryption key. Yeah, and so these are things one worries about. Okay, so the sorts of things you have to worry about is, well, if Alice is going to sign documents, can you get her to sign a very tricky document where signing it reveals her key? And so there's a lot of, this is something that people study a lot, and then, there are ways to make sure that it doesn't give away information. Yeah? Okay, so these are the sorts of things that you'd worry about in a course in cryptography or in security. Okay. Any more questions? Okay, should we take a 2-minute break and then we'll resume? Okay. So now, for the next couple of lectures, we are going to be talking about polynomials, and okay. So again, most of you have probably seen polynomials before in high school algebra, but the twist is, eventually, what we're going to be doing is we'll be working modulo prime. So we'll be working with polynomials, but we'll be working modulo prime. And once you put these two together, you get these very beautiful properties. So already polynomials have many, many beautiful properties. And then when you're working modulo prime, you get even more interesting properties. And these are what I use for error correcting codes, for secure ways of storing information, where the security is not against an eavesdropper, but it's against deletion or against noise. Okay, so let's go back and review some of the properties of polynomials. Okay, so what's a polynomial? A polynomial is something like, well, this is a polynomial, 2x minus 4. Right, that's a polynomial. It's a polynomial of degree 1. Another polynomial is x cubed plus 2x minus x squared minus 3x plus 5. Right, that's a polynomial. Okay, so it's this is a polynomial of degree 3 because that's the largest degree term there is. That's the highest power of x there is. These are all polynomials in one variable, and that's what we'll be talking about in this course. Okay, so now, of course, we can plot one of these polynomials. So if p of x equal to 2x minus 4, we can plot it at x equal to 0. It's minus 4. And then p of x equal to 0 at x equal to 2. And then this is a straight line, right? That's what... Right? I'm sorry? Not very straight, or? Okay. So... so this 2 is called a root of this polynomial, right? It's a value of x at which this polynomial is 0. So x equal to 2 is a root of the polynomial 2x minus 4. Okay. What other property does a line have? I'm sorry? It has one root. Actually, so as long as the polynomial is not 0, and if it's of degree 1, it has at most one root. Right? So if it's degree 1, and as long as p of x is not the 0 polynomial, right? In which case the plot would be the x-axis, and everything would be a root. As long as p of x is not 0, then has at most one root. How could it not have a root? Yeah, it could be parallel, right? It could be parallel to the x-axis. Okay. Here's another property of a line of this degree 1 polynomial. So if I give you the value of this polynomial at 2 points, then it determines the polynomial uniquely. Right? So if I tell you at this point 3, it takes on this value. So if I tell you that here it's this value, and if I also give you some other value, so for example, I tell you at 1, it takes on that value. So if I give you just these two values and leave off everything else, and I ask you, what's the polynomial of degree 1, at most 1, that goes through these 2 points? The claim is there's one and only one that goes through. So you can find one that goes through these 2 points, and there's only one that goes through. There's a unique one. Now, it turns out that these 2 properties, these are fundamental properties of polynomials, and they hold for any degree. Okay, so there's property 1, any non-zero polynomial of degree d has at most d roots. Okay, so with the line we were saying that's a special case d equal to 1, and now it's true for any d. Right? And then there's a second property, property 2, which is, suppose you're given the values at d plus 1 points. So suppose you're given the values that at x1 the value should be y1, x sub d plus 1 the value should be y sub d plus 1. Okay. Then there's a unique degree, there's a unique polynomial of degree d. Well, at most d. Which goes through these points, such that p of x sub I equal to y sub I, for I equal to 1 to d plus 1. Okay, so by the way, does anyone know why we said at most d, that the degree is at most d? Yeah. Yeah, no, so greater than, yes, but why didn't we say exactly d? Why did we say at most d? I'm sorry? Yeah. Yeah. The points may not be distinct. Okay, well, what if they were distinct? Yeah. I'm sorry? Yeah. So you see, you could have degenerate cases. So what if I, what if I were to take not 2 but 3 points on this line, and I were to say, find me a polynomial of degree at most 2 that goes through these 3 points. Okay, there's a unique one. If there's a unique one of degree at most 2, which one would it be? It would just be this line, right? Okay, and so even though you could have a higher degree polynomial, in fact, there's one of lower degree, and that's the only one there. So this is a degenerate case, right? If you pick 3 points, you don't expect them all to lie on a line, but there could be a case where they all lie on a line, and then that's what you have. Okay. Now, okay, this brings me to one other thing about polynomials. So roughly, roughly what you expect from a polynomial, well, what you expect is the degree sort of is a shorthand for how many times it wiggles around, right? So in other words, if you if you have polynomials like x squared minus 1. Okay, let's try to plot it out. So y equal to x squared minus 1. So at 0, it's minus 1. At 1, it's 0. And at minus 1, it's 0. And then it sort of goes up from there. So it's, right? So unlike a straight line, which is degree 1, it sort of wiggles. It goes down and then it comes up. And then at degree 3, what it might do is it might go down, come up, and go down again. Right? So at degree 3, it might actually do that. Right? So this might be x cubed. I know it's probably something like minus x cubed plus 3x squared plus minus 4x plus 1. Something like this. That might be a curve like that. And then we have x to the 4, it might wiggle once more. Right? So the degree is how complex it's getting. So the higher the degree, the more complex the curve gets. And this is why polynomials are used in graphics. Right? In trying to draw, to draw pictures in graphics, you use splines or these sorts of polynomials. Okay? These are extremely useful there. Okay, so let's see how you would prove property 2, given property 1. So there are two sides to property 2. Okay, so suppose I give you, I'm trying to figure out a polynomial. So suppose I want to find a polynomial such that which goes through the points 0, 1, 1, 2, 3, 5. Okay, so these are just points I want to go through. So I want P of 0 equal to 1, P of 1 equal to 2, P of 3 equal to 5. And I want a polynomial of degree 2. I'm guaranteed a unique polynomial of degree 2. So there are two questions. How do I find it? And secondly, why is it unique? Okay, so let's see how to find it. Okay, so in order to find it, let's first do a little puzzle. So okay. So the puzzle is this. Can you figure out this product? So here's a polynomial. Can you figure out what its value is? Anybody? It's no? Yeah. I'm sorry? It's 0, yeah, it's 0. Because there's an x minus x somewhere. Oh, sorry, that was bad. No? Okay, but that's, what could I do? That's the secret behind this. Okay. Okay, so the secret to solving this, finding this polynomial, is first we ignore that we want P of 0 equal to 1, P of 1 equal to 2, P of 3 equal to 5. Let's instead find a polynomial Q. It's always easier to find Q than P. So let's find Q such that Q of 0 equal to 1, Q of 1 equal to 0, and Q of 2 q of 3 equal to 0. Okay, so how would you find such a polynomial? Of degree 2. Yeah. You could set a system of equations. Yeah, but what else could you do? Yeah.
You could also like do x minus 1, x minus 2.
Yeah, you could look at the polynomial x minus 1 times x minus 3. Right? And why is that good? Well, that's when you substitute x equal to 1, you get 0. When you substitute x equal to 3, you get 0. What about when you substitute x equal to 0? You get 3. So now, what would you have qx be? Q of x equal to? This is 3 at x equal to 0. We want 1, so what should we do? Divide by 3. So that's it. Okay. So let's call this q sub 0 of x. And now let's repeat this process. So let's find q sub 1. This is q sub 0 of x. Q sub 1 of 0 equal to 0. Q sub 1 of 1 equal to 1. Q sub 1 of 3 equal to 0. Okay, so how do we do this? So what's q sub 1 of x? Now what do we want it to be? So we want 0 and 0, so what should we do? Yeah, x times x minus 3. And then we want q of 1 to be 1. So if we substitute by x equal to 1, we get 1 times minus 2. So we should divide by minus 2. And then similarly, we do q sub 3 of 0 equal to 0, q sub 3 of 1 equal to 0, q sub 3 of 3 equal to 1. And now q sub 3 of x would be x times x minus 1. And then we substitute x equal to 3, and we get 3 times 2 is 6, so we divide by 6. Okay? And now, what do we actually want? We want a polynomial p which is 1 at 0, 2 at 1, and 3 at 5. 5 at 3. Right? So how do we get that? How about if we take p of x equal to 1 times q naught plus 2 times q1 of x plus 5 times q3 of x. So first of all, is it the correct degree? Is its degree equal to 2? Yeah, because it's the sum of 3 degree 2 polynomials. Now what's its value at 0? 1, right? Because these two don't contribute anything to the value at 0. And this one contributes 1. Okay, what's its value at 1? It's got to be 2, right? Because these two don't contribute anything at 1. This one contributes 1 times 2. What's its value at 3? Well, again, these two don't contribute anything. This one contributes 1 times 5. Right? So we got the correct polynomial. Right? Okay. Now, you should be able to see that we didn't use the fact that this was degree 2 anywhere. Right? if it was degree d and there were d plus 1 points, we could have done exactly the same thing. Right? All we'd have had to do was create these functions q sub x1, q sub x2, q sub x3, up to q sub x d plus 1. Right? Or we could call them q sub 1 through q sub d plus 1, each of which was 1 in exactly one of those locations and 0 everywhere else. And then when we wanted to put together the polynomial p, we just take y1 times q1 plus y2 times q2, y3 times q3, and so on. Right? Because each of those was a polynomial of degree d, and we added them up, we'd get a polynomial of degree d. And then, on the point x1, only one of them would contribute. All the others would contribute 0. And what would it contribute? It would contribute 1 times y1. Right? So that's how it would work. Okay? So this process is called Lagrange interpolation. Okay, and it gives you a general way, given the value of the polynomial at d plus 1 points, of creating a polynomial of degree d such that it has those values. It goes through those d plus 1 points. Okay, now we also claim that this polynomial would be unique. Okay, so let's prove that the polynomial is unique. Okay, so claim polynomial p of x of degree at most d such that p of xi equal to yi, I equal to 1 through d plus 1 is unique. Such a polynomial is unique. So we already showed how to find one such polynomial. Now we're claiming there's only one such polynomial. Right? Once I give you the d plus 1 points, there's one and only one such polynomial. So how do we prove it? Proof. Suppose for contradiction, there exists also a p prime of x, also of degree at most d, which goes through all these points. Now let's look at p of x minus p prime of x. Okay? So this is a polynomial of degree d. And what's its value at x? It's not equal to 0. It's not identically 0 because p and p prime are different polynomials. Right? But now what do we know about it? What's the value of this polynomial at the point xi? So let me call this polynomial r of x. So what's r of x sub I? It's 0. For I equal to 1 through d plus 1. So here you have a non-zero polynomial of degree at most d, and it has d plus 1 roots. That contradicts property 1. Okay? So as long as you believe property 1, we've proved property 2. Now, there's one last observation before we stop here, which is in order to prove all these properties, in order to reconstruct the polynomials through interpolation and to prove these properties, all we use about these numbers, the numbers we are working with, is that we can add, subtract, multiply, and divide. We can divide when the number is not 0. Right? These are the only properties we are using about the numbers we are working with. Okay, so the properties we use is we can add two numbers, we can subtract, we can always multiply, and we can divide as long as we are not dividing by 0. Okay. What we are going to do next time is we are going to say, well, since these are the only properties we are using, we can also do our arithmetic modulo a prime. Because when we do arithmetic mod p, we can always add numbers, we can always subtract, we can always multiply, and the only thing that's not relatively prime to p is 0, right? Among the numbers from 0 to p minus 1. And so we could just as well do our arithmetic mod p, and we could just work with polynomials and have these properties. Okay, so that's where we are going next time. Okay, see you then.